This is basically the second reading for the JIT for this week 2, which is covering basically talking about temperature scales and thermal expansion and so on. So the idea is the first thing that it covers really is, well, how do you actually define a temperature anyway? And this is kind of an unstated law, but the idea is that if you measure an object A by bringing the thermal equilibrium with, say, a thermometer, and you know exactly what the temperature is, and then you measure object B with the thermometer, and you know what the temperature is. If A and B are separately in thermal equilibrium with a third object, which essentially is the thermometer C, then if you put A and B together, they're in thermal equilibrium with each other. The idea is that this is what really determines what a temperature means, and then also what thermal equilibrium means. The idea is if you have two objects A and B that are thermally in contact, if one object is hotter than the other, say B is hotter than A, then energy naturally flows essentially from the hot object to the cold object. This is what we're going to eventually be getting to. But the idea about a thermometer, which we use all the time, is that we use some property of some material in order to measure the temperature. And so, for example, a mercury thermometer essentially looks at the thermal expansion of the mercury as it gets warmer, and it essentially takes up more volume, and so it goes up a capillary tube. And so you can tell basically what the temperature is by how much the mercury has expanded. Also more common sort of temperature way of measuring the temperature, and I think you guys did this in your laboratory, is that if you have a gas, and it actually doesn't matter as long as these are ideal gases, meaning that the density is not too terribly high, so that the interaction, basically the atoms of the gas don't interact with each other. Then if you have a gas which is where the volume is constant, as you lower the temperature, the pressure decreases. This is just what you learn in chemistry from, the pressure times the volume is equal to, nRT, which is what we're going to talk about here again as well. But the idea is you lower the temperature, then the pressure decreases at a constant rate. And no matter what your starting pressure is, say for a given volume, they will all extrapolate out essentially to zero pressure at some well-defined temperature, which is minus 273.15 degrees Celsius. And this temperature is what really is defined as absolute zero. The Fahrenheit scale, which is most commonly used, which you're used to, is where the temperature of the freezing point is 32 degrees Fahrenheit and the temperature of the boiling point is 212 degrees Fahrenheit, and there's 180 divisions between the 2 points. 0 degrees Fahrenheit, by an odd circumstance, was in basically before about 1860, where they actually started making refrigerators. This was the coldest temperature that one could manage by mixing essentially ice with a salt brine solution. So you put salt on it. Like when you make ice cream, you put salt over ice and it lowers the temperature to almost exactly about 0 degrees Fahrenheit, which is kind of odd. The degrees Celsius scale is much more rational in that it basically, if you take an ice-water mixture, it's defined as 0 degrees C. This is essentially at the dividing line where if it's at any lower temperature, water freezes. So this is at atmospheric pressure. And the temperature of where it can, basically changes into water starts boiling at 100 degrees C. This is the boiling point of water. So you use two physical properties, the freezing point of water and the boiling point of water, and divide it up into 100 equal segments. This is what is defined as the Celsius scale. And then the one which we may not be quite so familiar with, except in chemistry, is that since all ideal gases basically extrapolate to zero pressure at minus 273.15 degrees C, we just define a new temperature scale where that's now absolute zero, which is the coldest temperature that you can achieve. And in fact, you can't really achieve absolute zero. The coldest temperature at this point in time is where you use laser cooling, and they can get down to about a nanokelvin, which is about 10 to the minus 9 Kelvin. But that's the lowest temperature that anyone has achieved. In fact, that temperature is essentially limited by the 0 point motion, for a quantum oscillator, because essentially it's impossible to get a quantum mechanic system to essentially cease, because if it did, you would know exactly where it was, and Heisenberg uncertainty principles makes it so that you can't do that. So you define this as 0 degrees Kelvin at absolute zero at minus 273.15 C, and then you define it so that the segment degrees Celsius is exactly the same as the change in degrees Kelvin. So it allows you to convert between this. And so what that means is 0 degrees C is 273.15 Kelvin. Now the idea is that the other thing that you can use essentially is as you raise the temperature, almost all materials expand as you raise the temperature, which makes a certain amount of sense, because what we're going to be getting to is that temperature is essentially a measure of the amount of energy associated with the material, and so atoms tend to vibrate as they increase their temperature, and so at higher temperatures they vibrate more, and so what naturally happens is they tend to get farther, the atoms from atom to atom tend to get farther apart as you raise the temperature, and so the object as a whole tends to expand. So it turns out over large temperature ranges that the expansion of an object along a line is linear with temperature. So if you have a 10 degrees C change to higher temperature, it expands by a certain amount. And if you double the amount of temperature change, say to 20 degrees C, then the expansion is about twice as much. And of course it depends, just like when we talked about stresses and strains, it's a relative change of the length and depends on how much material you have. The longer the initial material is, then of course naturally it will expand longer. So it's a fractional change. But these temperature coefficients, alpha, the linear expansion coefficient, this is basically associated with a particular object. So for example, quartz doesn't expand nearly as much as most metals, like copper or aluminum or gold. And so these are very different for different materials. The final thing that is that obviously if they expand along one dimension, then they expand along 2 dimensions. So you can have an areal expansion or you can have a volume expansion. And so for particular water is highly unusual in that as you lower the temperature it becomes more dense. But for some very odd reason, the highest density of water occurs at about 4 degrees C. What that means is that if you look at, say, as you cool down water to close to 0 degrees C, once it gets to 4 degrees C, the most dense water is at 4 degrees C, and that tends to fall to the bottom of the lake, say, for example, whereas any colder water at the surface essentially will stay at the surface. And this is why, essentially, and for no other reason, that when water freezes, it tends to freeze at the top of the surface of the water, mainly because the heat transfer to the outside air goes through the top surface of the lake. And since the colder water, once it gets below 4 degrees C, it occurs at the surface, that's where the ice will first form. If that weren't the case, then obviously it would make things very difficult for any fish that were in the water, because it would freeze at the bottom of the lake instead of the top. And the maximum density of water is 1,000 kilograms per meter cubed at about 4 degrees C. It doesn't change by very much, but it does change a little bit. So now what you do is you go through some practice questions talking about thermal expansion, and then we'll get back.